This video will cover periodic trends in acid strength for binary acids and oxoacids. A binary acid consists of hydrogen and one other element. An oxoacid contains hydrogen, one or more oxygens, and a central element. With oxoacids, the acidic hydrogen is bonded to an oxygen, and the oxygen is attached to the central element. Before we can compare acid strength, we need to define what we mean by a stronger acid. But let's start with what a stronger acid is not. When we refer to a stronger acid, we are not talking about a more concentrated one. A stronger acid is one that leads to more H+ in solution. So an acid that undergoes dissociation more readily to form products, H+ and the conjugate base, is a stronger acid. For a weak acid, we can think about the mass action expression. For a stronger acid, the numerator of the mass action expression is larger, and a stronger acid leads to a higher value of Ka. A higher value of Ka corresponds to a lower value of pKa. Ka and pKa are inversely related. The next thing we need to do is identify the type of acid, binary or oxo. This is really important, mainly because of how electronegativity is related to acid strength. Again, a binary acid has hydrogen and one other element. An oxoacid has hydrogen, oxygen, and another element. The periodic trends are shown in these diagrams. A binary acid is stronger going across a row to the right because of the greater difference in electronegativity between hydrogen and the other element that we're calling X. This greater difference in electronegativity makes the bond more polar, which means the electrons are not evenly distributed and are sitting closer to the other element. This makes it easier for the H+ to dissociate, which leads to a stronger acid. The periodic trend up or down a column for a binary acid is not based on electronegativity. This is the common mistake, so I'll repeat it. A binary acid's strength is not based on electronegativity moving up or down a column. It is based on the size of the element X. Atomic size increases moving down the column, and a larger atom means there is a larger distance between the nucleus and the valence electrons bonded to the hydrogen. This increased distance leads to a weaker bond, which makes it easier for the H+ to dissociate. And increased dissociation corresponds to a stronger acid. For oxoacids, the periodic trend in both directions is based on electronegativity of the central atom X. So acid strength increases up a column and to the right across a row. The atoms are bonded in order of XOH. If X has a higher electronegativity, then it pulls on the electrons more strongly and creates an inductive effect. This means electron density in the OH bond is influenced by this long-range effect, and the electrons will be pulled closer to the oxygen based on the electronegativity of X. This decreases the strength of the OH bond, which makes it easier for the H+ to dissociate, which leads to a stronger acid. The other trend we see with oxoacids is related to the oxidation state of the central atom. If the number of oxygens increases, then the oxidation state increases. If the only difference in an oxoacid for the same central atom X is the number of oxygens, then a greater number of oxygens leads to a stronger acid. This has to do with the stability of the conjugate base. If we remove an H+ from an oxoacid, by definition, we are left with the conjugate base. If that conjugate base has more oxygens versus fewer oxygens, then it can better distribute the negative charge across the molecule, leading to a more stable conjugate base. So more oxygens means a more stable conjugate base. Because a more stable conjugate base is stable, it is less likely to react because it's stable, which means it is less likely to accept an H+. If a conjugate base is less likely to accept an H+, then it is a weaker conjugate base, and a weaker conjugate base corresponds to a stronger conjugate acid. So our strategy is, first, identify the acid type, binary or oxo, then determine what is the trend. Are we looking across a row, up or down a column, or simply at the number of oxygens? And finally, we'll predict the relative strength. And it turns out there are only 3 things that we have to look at: electronegativity, size, or number of oxygens. So we'll work through a few examples and we'll apply those 3 steps of that strategy in order each time. So in this example, we are comparing HCl and HBr. So the first step is we identify if the acids are binary or oxo. We notice there is only hydrogen and 1 other element in each acid, so these are binary acids. The next thing we need to do is determine what are we comparing. We're comparing Cl versus Br, and we need to take a look at the periodic table to see if that comparison is across a row or up and down a column. And we find chlorine and bromine right here, and we're looking up and down a column. The last thing we need to do is to make our final assessment. So we noticed that bromine is lower on the column compared to chlorine. Because it's lower in that group, it means that bromine has a larger size compared to chlorine. And the larger size means that there's a weaker bond for HBr versus HCl. And this weaker bond means there's increased likelihood of dissociation, which corresponds to a stronger acid. So the stronger acid in this pair is HBr. In our next example, we are comparing H2SE versus HBr. The first thing we do is identify the type of acid, and these are binary acids. The second thing we do is determine what trend we're looking at, and we have selenium versus bromine. So we need to take a look at the periodic table to see what our comparison is. So here we have selenium and bromine, and we see that they're part of the same row. So the trend that we're looking at is across the row. So in this example, we are comparing electronegativity. So bromine has the higher electronegativity compared to selenium, which means it will create a more polar bond with the hydrogen, and a more polar bond means it's easier for the H+ to dissociate. So there's increased dissociation. And increased dissociation means that we have a stronger acid. So in this example, hydrobromic acid is the stronger acid compared to hydroselenic acid. In our next example, we are comparing hypochlorous acid to perchloric acid. We're going to continue to follow our strategy. So the first thing we're going to do is identify whether the acids are binary or oxo acids. And they are oxo acids because we have hydrogen, oxygen, and a central atom, which is chlorine. The next thing we do is determine if we're looking at a trend across a row, up and down a column, or the number of oxygens. And we can see here very clearly that we're looking at the number of oxygens. So the next thing we have to do is determine which acid is stronger based on that argument. So the argument is, as we increase the number of oxygens, we are increasing the stability of the conjugate base for perchlorate versus hypochlorite. So perchlorate is more stable. Because perchlorate is more stable, it is also the weaker base. So the more stable conjugate base corresponds to the weaker conjugate base. And a weaker conjugate base corresponds to a stronger conjugate acid. So in this example, our stronger acid is perchloric acid. In this example, we first identify the type of acid. We can see that they are oxoacids. The next thing we do is identify what trend we're looking at. These two acids have the same number of oxygens, so that's not a means of comparison. So we have to compare the central atom. So we're looking at phosphorus versus sulfur. So we'll take a look at the periodic table. So we find phosphorus and sulfur, and we are looking at a trend within a row. So we have an oxoacid, and we're looking at the trend within a row. The justification for the periodic trend with an oxoacid is always based on electronegativity. So because sulfur is further to the right, there's a higher electronegativity for sulfur. Because there's a higher electronegativity for sulfur, it makes the OH bond more polar in the acid containing sulfur. And because that bond is more polar, it means that it is weaker. So that weaker bond means that it is easier for that H plus to dissociate, and a greater extent of dissociation means that we have a stronger acid. So the stronger acid in this example is sulfurous acid. And in our final example, we identify the acids as oxoacids. The number of oxygens is the same, and so we are comparing the central atom. So here we have phosphorus versus nitrogen. So we'll look to the periodic table to see what the trend is, how they compare. Finding nitrogen and phosphorus, we see that they are part of the same column, part of the same group. So we have oxoacids that we are comparing up and down a column. All periodic trends of oxoacids are based on electronegativity. Nitrogen is higher in the column, and so there is a higher electronegativity for nitrogen. Because nitrogen has a higher electronegativity, there is a greater induction or inductive effect that makes that bond, that OH bond, more polar. So there's a more polar OH bond in the nitrogen-containing acid, and that more polar bond means there is a weaker bond. And the weaker bond means it is easier for that hydrogen, the hydrogen ion, to dissociate, which leads to a stronger acid. So in this example, the stronger acid is nitric acid.